The three-phase inverter essentially given input side a single a DC. In this experiment, we will be demonstrating three-phase inverter, its functionality. The three-phase inverter essentially given input side a single a DC supply, whereas output side you will get the three-phase AC supply. And in this case, output voltage as well as frequency both are controllable in case of three-phase inverter. Whereas in case of conventional three-phase supply, the voltage magnitude we can able to control, but there is no control on the frequency. The frequency is 50 Hz in the normal operating condition, and voltage is 440 volts three-phase AC supply. So here, by using the three-phase inverter, and if you have a DC supply, we can able to generate three-phase AC supply where the magnitude as well as frequency is controllable. So since the magnitude as well as the frequency both are controllable, this kind of inverters are more suitable for the drives, AC drives, where we need to control the voltage to frequency ratio constant value. The circuit diagram is shown here. We begin with the single phase AC supply, and this single phase AC supply is connected to diode bridge rectifier via auto transformer. So by using auto transformer, we can able to adjust the bridge rectifier AC supply voltage, and finally we can able to control the DC input voltage given to the inverter by using the auto transformer. So in the experiment, we will be demonstrating two different voltages. 75 volts DC bus voltage and another one is 100 volts DC bus voltage we will give, and we try to see the what are the AC waveforms on the load side, and what are the different harmonic components present in the line voltages on the AC side. So the single phase three phase inverter is a IGBT based inverter which we will be using for the testing purpose. This IGBT inverter containing 3 legs, and each leg contains 2 switches. So the switching sequence is given here. Top leg contains devices 1, 3, 5. Bottom leg contains 4, 6, 2. And the load terminals are connected to 3 load terminals indicated here R, Y, B. So these R, Y, B terminals goes to the 3-phase load. So this is a 3-phase load where you can see the load is connected in the star fashion, and here load we are assuming identical load R, and before that there is a inductor and capacitor. So 3 capacitors are connected across the load, and 3 inductors are connected in series with the line. So this filter LC is going to act as a filter, and if you give the square waveform here, in this case pulse width modulated square waveform, we will get the across the load sinusoidal voltage. Okay, so here before the load and in between the inverter output terminals and load, we are connecting an LC filter, which essentially to realize the sinusoidal voltages, line voltages, which are going to apply the line terminals of the 3-phase star connected load. Now if you want to make the entire system to be functional, there are a few things that we have to set first. The first important thing is we need to give the gating sequence for the devices. The device number is given according to the gating sequence. So we are going to demonstrate 180 degrees conduction of this inverter. In 180 degrees conduction mode of operation, each device is on for 180 degrees, and after every 60 degrees the new switch is going to be turned on. So in this case we begin with switch S1, assuming that it is gated starting from 0 degrees. After 60 degrees switch 2 is given pulse for a duration of 180 degrees. Then after 2 we will be giving gating signal for the switch 3 and then subsequently 4, 5, 6. So using this gating scheme we can able to generate three phase balanced voltages across the load terminals R, Y, B. So first I will be showing this is the beginning. AC supply is given to the auto transformer. The auto transformer input is given to the diode bridge rectifier, and this is a single phase diode bridge rectifier. Here you will be getting the DC supply voltage. So in the process of experimentation, we will adjust the auto transformer voltage such that DC output voltage is set to 75 volts. So you can see now the DC link voltage is set to 75 volts. From here to now the three-phase inverter firing scheme generated by the FPGA board. Okay, and this FPGA board is going to generate the three-phase what is called gating scheme for the IGBT inverter, and using this we can set two important indexes. One is frequency. Okay, and we can also set the modulation index. And this programming is done that whenever I change the frequency, the modulation index also is going to change. So modulation index for this program, the program is made such that modulation index maximum of around point frequency, modulation index is also changing. So the maximum modulation index and frequency achievable through this one is 58 and modulation index is 0.85. Okay, start. So this is a three-phase inverter module. You can see the three-phase inverter module, and there are bridge is shown here. There are six switches are connected. In each leg two switches, and you have a DC bus capacitor also, and the sequence also is given here. So this is you can see inside various devices, but it is not so clear enough to understand. So this is the entire three-phase bridge module. The gate pulses are generated from the FPGA module are given here. Just internally you can see the green colored cards are there. They are the IGBT drivers for leg 1, leg 2, leg 3. So each card is meant for generating the gating scheme for one leg of switches. So you can see on the screen, oscilloscope screen, channel 1, 2, 3 are corresponding to three-phase line voltages. You can see these three line voltages, peak voltages are identical, and three voltage waveforms, line voltages are displaced by exactly 120 degrees. So since the peak voltage as well as the angle, phase angle difference is 120 degrees, these voltages are going to constitute a three-phase balanced supply. Whereas one line voltage is shown here, that is before the filter, and this is not going to be a sinusoidal because we are using a single phase three-phase inverter, and due to the switching scheme, it depends on the type of PWM adapted. The waveform is not going to be sinusoidal. If you want to achieve the sinusoidal voltages and currents, we have to use the filter. So channel 1, 2, 3 are going to indicate the balanced voltages after the filter. So this is a three-phase filter bank set. So you can see the three inductors which are connected in series each line, L1, L2, L3, and there are three capacitors are there, C1, C2, C3, which are connected in the star fashion, and neutral is also present in this. So three inputs are coming here, R, Y, B, and the outputs are given to the load. So load is three-phase resistive load bank is here. By changing these knobs, I can change the load. So in this experiment, we will be taking couple of measurements by setting the DC link voltage and modulation index. Your job is to note down the uh, load magnitude, DC bus voltage and DC bus current, uh, RMS load voltage, fundamental magnitude, load current and THD. So among all these, you should pay attention for the load side, three phase AC voltage, RMS voltage and THD, how it is varying with modulation index and at different frequencies along with the load.
Now we will note down the observations. Initially we have set the DC voltage to 75 volts and the frequency has been set to 50 hertz and modulation index is 0.85. Now we will record the other observations on the basis of the load. We have set the load to 118 ohms. Now the DC current is 0.1 amperes. Sorry, DC current is 0.1 amperes. The output voltage is 37.92 volts. The output current is 21.9 milliamperes. The fundamental component of output voltage is 37.87 volts and THD is 2.2%. Now we will change the load. As you can see, the the source current has changed. Now the source current is 0.28 amperes. The output voltage is 36.82 volts. The output current is 41 milliamperes. The fundamental component of output voltage is 36.72 volts and THD is 1.6%. Now we will change the load again, and the load now has been set to 43 ohms. You can see the input DC current has changed again. Now the current is 0.44 amperes. The output voltage is 36.20 volts. The output current is 61 milliampere. The fundamental component of output voltage is 36.12 volts and THD is 1.8%. Now we will change the load again. We will increase the load, and now the load is now 31 ohms. The input DC current is now 0.6 amperes. The output voltage is 35.59 volts. The output current is 80.6 milliamperes. The fundamental component of output voltage is 35.56 volts. THD is 2%. We will change the load again. Now the load has been set to 25 ohms. As you can see, current has changed. The input DC current is now 0.76 amperes. The output voltage is 35.15 volts. The output current is 99.8 milliamperes. The fundamental component of output voltage is 35.16 volts and THD is 2.3%. Now we will take another set of readings where frequency has been set to 40 hertz. Modulation index is 0.69 and input voltage is same, that is 75 volts. Now we will again change the load. Load is now set to 118 ohms and the source current is now 0.8 amperes. 0.08 amperes. Now the output side observations. The output voltage is 30.89 volts. Output current is 18.7 milliamperes. The fundamental component of output voltage is 30.80 volts and THD is 2.8%. Now we will again change the load. The load is now changed to 58.7 ohms and current is 0.2 amperes. The output voltage is 30.08 volts. The output current is 34 milliampere. The fundamental component of output voltage is 29.9 in 30 volts. The fundamental components of output voltage is 30 volts and THD is 2.1%. Now we will again change the load. Load is now set to 43 ohms. The input side current is now changed to 0.3 amperes. The output voltage is 29.57 volts. The output current is 50.2 milliampere. The fundamental component of output voltage is 29.52 volts and THD is 2.2%. We'll again change the load. Load is now set to 31 ohms. The input side current is 0.4 amperes. The output voltage is 29.14 volts. The output current is 65.8 milliampere. The fundamental component of output voltage is 29.09 volts and THD is 2.4%. The load is now set to 25 ohms and the input current is now changed to 0.5 amperes. The output voltage is now 28.83 volts. Output current is 81.9 milliampere. The fundamental component of output voltage is 28.77 volts and THD is 2.9%. Now we will record the third set of readings. Here frequency is kept to 25 Hz and input source voltage, input DC voltage is kept at 75 volts. The modulation index is 0.43. Now we have set the load at 118 ohms. The input side current is 0.04 amperes. Voltage is 18.23 volts. The output current is 13.7 milliampere. The fundamental component of output voltage is 18.18 volts and THD is 3.2%. Change the load again. Load is now kept at 58.7 ohms. Now the input side current is 0.08 amperes. The output voltage is 17.69 volts. The output current is 21.6 milliampere. The fundamental component of output voltage is 17.67 volts and THD is 2.7%. The load has been set at 43 ohms. The source side current is now 0.1 amperes. The output side data is now output voltage is 17.4 volts. Output current is 30.7 milliampere. The fundamental component of output voltage is 17.3 volts and THD is 2.8%. Now the load has been set to 31 ohms. The input side current is now 1.4 amperes. The input side current is 0.14 amperes. The output voltage is 17.15 volts. The output current is 39.8 milliamperes. The fundamental component of output voltage is 17.12 volts and the THD is 3.3%. Is the load again. Now the load has been set to 25 ohms. The input side current is now 0.18 amperes. The output side data is output voltage is 16.99 volts. The output current is 49 milliamperes. The fundamental component of output voltage is 16.92 volts and THD is 3.6%. Now we will record the last set of observations. In the previous 3 sets, the DC voltage has been kept at 75 volts. Now we will have set the DC voltage to 100 volts and frequency is kept at 50 Hz and the modulation index is 0.85. Now we will record the other observations for in the load. So initially we have set the load at 118 ohms and the input side current is 0.14 amperes. Voltage is 52.9 volts. The output side current is 28.7 milliampere. The fundamental component of output voltage is 52.5 volts and THD is 2.1%. The load is now set to 58.7 ohms. The input side current is now 0.4 amperes. The output side data is now output voltage is 51.4 volts and the output current is 56.3 milliampere. The fundamental component of output voltage is 51.1 volts and THD is 1.4%. Now 4.4 milliamperes. The fundamental component of output voltage is 50.2 volts and the THD is 1.6%. Now we will change the load again and we will set the load at 31 ohms. Now the input side current has changed to 0.84 amperes. The output data is the output voltage is 49.6 volts. The output current is 112.2 milliamperes. The fundamental component of the fundamental component of output voltage is 49.5 volts and THD is 1.8%. Now we will change the load again. And now the load has been set to 25 ohms. The current has been changed to 1.4 amperes. The output voltage is now 49.1 volts. The output current is 139.3 milliamperes. The fundamental component of output voltage is 48.9 volts and THD is 2.3%. Hello. Is there any query regarding this experiment? Hello, am I audible?
Yes, ma'am.
Is there any query? Actually, we want to show one more experiment. Boost converter. So we can take a gap of 10 minutes and then we will start that video also. Okay, repeat the readings for the last set.
Boost converter is the 5th experiment, ma'am, right?
Right. And one more thing, on Monday, who are the students who did the class on Mondays? Are you the same batch who used to do the class on Mondays?
It's not
The fundamental
exactly
component
same.
of output voltage is 17.67 volts and THD 0.23 volts. The output current is 13.7. Current is point set. दोबारा बोलूँ ना. Now at 75 volts, the modulation index is 17.67 volts and TH output voltage is 1.4 amperes, which is 17.3 volts, and THD is 2.8%. Now the load has been set to 31 ohms. Current is now 0.1 volts and THD is 17.67 ohms. Now the output voltage is 18.18 volts ampere. 0. Now at 75 volts, the modulation 3.3%. Is the load again. Now the load has been set to 25 ohms. The input side current is now voltage has been kept at 75 volts. Now we have set the DC voltage to 100 volts and frequency is kept at 50 hertz and the modulation index is 0.85. Now we will record the other observations for in the load. So initially we have set the load at 118 ohms and the current, the input side current is 0.14 amperes. Voltage is 52.9 volts. The output side current is 28.7 milliampere. The fundamental component of output voltage is 52.5 volts and THD is 2.1%. The load is now set to 58.7 ohms. The input side current is now 0.4 amperes. The output side data is now output voltage is 51.4 volts and the output current is 56.3 milliampere. The fundamental component of output voltage is 51.1 volts and THD is 1.4%. Now 4.4 milliamperes. The fundamental component of output voltage is 50.2 volts and the THD is 1.6%. Now we will change the load again and we will set the load at 31 ohms. Now the input side current has changed to 0.84 amperes. The output data is, the output voltage is 49.6 volts. The output current is 112.2 milliamperes. The fundamental component of the fundamental component of output voltage is 49.5 volts and THD is 1.8%. Now we will change the load again. And now the load has been set to 25 ohms. The current has been changed to 1.4 amperes. The output voltage is now 49.1 volts. The output current is 139.3 milliamperes. The fundamental component of output voltage is 48.9 volts and THD is 2.3%. Hello. Now we will take a gap of 10 minutes and then I'll start the video of boost converter. Okay.